Okay, so right now we're starting to look at something called exponential growth and exponential decay, okay? So yesterday we were identifying linear and quadratic. We really only looked at linear and quadratic. I mentioned that exponential would be coming, okay? So we're starting to look at exponential today. So exponential growth looks like the graph on the left-hand side. So you can see it's increasing at sort of a slow rate, and as time goes, it starts to get steeper and steeper and steeper, okay? Exponential decay is on the right-hand side. It's the opposite, right? So it starts steep and it slowly decreases, okay? What are some examples of real life that would match these types of graphs?
Population growth for the left.
Population, yeah. So I'm going to do exponential. I'll put exponential growth. And then we'll do decay over here. Okay, depending on the area, right? Population depending on the area. A lot of like African countries, you're going to see exponential growth. India, you might see exponential growth. Canada, not as, it doesn't blow up as quickly, right? But we'll see population growth. Okay. Okay, so I'm going to not even lifespan, but have you ever heard of like lifespan of a like element, like an atomic element, like in science,
Yeah.
how they decay like that? That is exponential decay. Okay, so atomic decay. As maybe this isn't super a lovely way to think of it, but exponential growth cancer cells, right? That is ultimately what happens. You have 2, then you have 4, then you have 8, then you have 16. They're exponentially growing,
Yeah.
okay? Cancer cells. So that's okay for some examples. Okay, so the equation that makes an exponential growth or decay looks like this. So exponential growth is y equals 2 to the exponent x. X is the variable exponent, okay? So we're actually going to be plugging in different numbers for the exponent in this case. And 2, the number here is bigger than 1, okay? So it's bigger than 1 because it's growing.
Yeah.
Okay, exponential decay, it's y equals 1/2 to the exponent x. X again is your variable, and the number here is going to be between 0 and 1. Okay? The reason we're looking at this is because eventually we're going to be creating our own exponential growth and decay questions. So what you want to remember is if in the question it is exponentially growing, the base, and these are called the base, right? The base in a growing question, the base has to be bigger than 1, okay? And in a decay question, the base has to be less, between 1 and 0, okay? It's going to be a decimal or a fraction, okay? So that's just something to keep in mind. Okay, so we started doing this yesterday, and now we're going to continue. So Sandor drew cards from a standard deck of 52 playing cards until he drew a heart. He repeated this experiment many times. Each time, Sandor recorded the number of cards he drew before drawing a heart. For example, if he drew a heart on the first draw, then he drew 0 cards before he drew a heart. This happened 50 times as shown in the chart below. Okay, so they created a frequency chart. Alright, but basically all he's doing is he was drawing cards out of a deck. He was counting how many cards he had to draw before he actually got a heart. Then what they did is they sort of did a chart and say, how many times did he get the heart the first time? Well, got that 50 times. How many times did he have to draw 1 card before he got a heart? Well, that happened 30, and so on, okay? So they just created this frequency chart based on what actually ended up happening as he was doing this experiment. Calculate the first and second differences and ratio between consecutive pairs of frequencies. Does the relationship between frequency and the number of cards appear to be linear, quadratic, or exponential? Okay? So, first things first. We know what we're going to do for first differences is we're going to take this second number and subtract. Everyone agrees with that? I'll get back the calculator. Sorry. Again, this is the modeling chart on the front. No problem. You have your own calculator, right? Okay. What do you want? Okay. This will walk you through on the left-hand side how to calculate. So for our first difference, we're going to go 38. 38 subtract 50, and I got negative 12. Then I'm going to go 28 subtract 38, and I get negative 8. Then I'm going to go 21 subtract 28, and I get negative 7. 16 subtract 21, and I get negative 5.
28 subtract 38.
Oh, sorry, am I not paying? Let's start this again, shall we? Sorry, 38 subtract 50 is negative 12. 28 subtract 38 is negative 10. Right?
Yeah.
21 subtract 28, I must have just gotten my numbers, my lining off. 7, right? Negative 7. 16 subtract 21 gives me negative 5. Oh, it's just that one I must have. 12 subtract 16 is negative 4. And 9 subtract 12 is negative 3. Did I get it right the second time around?
Yeah.
Okay, sorry. I am human. I look at the wrong numbers. So, Stephen, we're just working on, you know where we're on. Okay, second differences are based off of my first differences. So for my second differences, I'm going to do this here. I'm going to try to write this really small, or actually what I'm going to do is I'm going to bring it over here so you remember. It's going to be negative 10 subtract negative 12. Okay, this is generally because I have all these negatives where I'm using my brackets. So in this case, I'm going to get 2. Then my next one's going to be negative 7, bracket, negative 10, close bracket, and I got positive 3. Then negative 5 minus bracket, negative 7 bracket, 2. Negative 4 bracket, minus bracket, negative 5. And then 1 again, right?
Yeah.
Okay, so my first differences are not a consistent number. Does everyone agree? They are not consistent.
Yeah.
My second differences are not a constant number. Everyone agree?
Yeah.
So now I have to go to my ratio, okay? If you come over here, your ratio goes back to your y value, okay? In this case, it's your frequency. And you are going to go the second number divided by the first. The second number divided by the first. So, here, it should be 38 divided by 50. Keep a couple decimal places here because you're looking for most consistent. If you round to one decimal place, you're not going to see if it's constant or not. So 0.76. Okay, then I'm going to go 28 divided by 38.
So 0.74.
0.7. I'm going to just do 36 or 37. I'm just going to keep a couple decimal places. Really, my consistency here is if I keep getting 0.7, 0.7, 0.7. Okay? Because that's close. Sorry, now I'm 21 divided by 28. 0.75. 16 divided by 21. 0.762. 12 divided by 16. 0.75. And 9 divided by 12. 0.75. Now again, I'm not showing all this math on the lesson because on the left-hand side there is a poster. And what it says is ratio. If the number is approximately constant, then it is exponential. Because I see the 0.7, 0.7, 0.7, 0.7, 0.7, that is fairly close, approximate. So we know that this question is an exponential. Okay, therefore, exponential. Does that make sense? Okay, now that modeling poster on your left stays up the whole time. Okay, so you'll be able to use that as a reference point. That being said, the more of these questions you practice, you won't even need to look at that, right? Because it'll just become, you'll just be used to it. Good? Yep.